This is a video of me documenting my proudest mathematical achievement, which is a formula for expressing a plus bi raised to c plus di, because on its own that's quite unruling. So, the first thing you need to remember is that e to the ln x equals x. That's very poorly written, but I don't really need to write it well, so that means we can raise e to the natural log of this number, which should be the exact same thing, right? Good thing about doing this way is with logs and natural log especially, well not especially, but basically with logs you can bring out the power, so we can take out the c plus di there, and then if we just ignore that, we're now faced with this problem, the natural log of a plus bi. In order to solve this, we need to remember that complex numbers are just points on a complex plane, which is a plane in which one axis is described by complex numbers, imaginary numbers, one is described by real numbers. So this can be described as a plus bi, or it can be described in terms of this line here. This line has a magnitude and an angle. We're going to call that magnitude m, and the angle theta. I know it's not technically that symbol there is not technically a theta, but it'll do. My font doesn't have a theta. So this allows us to describe, using the conversion between Cartesian and polar coordinates, a plus bi as these values. We use the cosine theta plus I sine theta according to Euler's identity is equivalent to e to the I theta, so that's why we're doing that there. So we now have a plus bi equals e raised to the I theta plus natural log of m. That makes sense. So, since we have to take the natural log of this, we can move this over to inside of a natural log, which just gives us out I theta plus the natural log of m. Now, since m equals root a squared plus b squared because Pythagoras, we can shove that like in there into the natural log and square root and just raise into the half power. So if we put that there, because it's inside of a log, we can bring it out. Right, and now theta is arctan of b on a due to tan being opposite divided by adjacent in the ratio. So if we shove that in, we get this unruly thing. Don't worry, it gets worse. So we now get e to the natural log of a plus b plus ci equals I times tan of minus 1 of tan to the minus 1 of b on a plus natural log of a squared plus b squared times a half times c plus di. It's disgusting and unruly, we know. So if we just ignore these things for now and we work with this double bracket, we can expand it to this. I know, awful, but it gets better, don't worry. So this is made up of two different things that look very similar, if you see at the top. We set these equal to omega and theta. Again, that's not an omega and that's not a theta, it's the best I could do. We can simplify that disgusting e to the power of something to just e to the power of omega plus I theta, which is the same as doing this, e to the omega times e to the I theta, and since according to Euler's identity e to the I theta equals cosine theta plus I sine theta, we can write it as that. So we get to a final point of a plus bi raised to the c plus di equals e to the omega times cosine theta plus I sine theta, when omega equals d on 2 times the natural log of a squared plus b squared minus d times arctan of b on a, and theta is equal to c on 2 times the natural log of a squared plus b squared plus c times the arctan of b on a. Disgusting, but you know, it's quite cool anyway, who cares? See ya.